Good afternoon, everyone, and welcome to our last day of AI training with AMD. I'm Sima as part of CASTIEL 2 project. I would like to open this session last day. I would like also to thank our organizers from NCC France as part of EuroCC 2 project, also AMD team and the experts. Thank you very much for your time and being here and your effort. So I'm now giving the floor to our experts and welcome back, and we are here. Okay. Thank you.
Thank you. Okay, let's go ahead and start off the day. First of all the materials we have shared are public materials. You are welcome to share them further or use them in the way you need. Please do not add any comments to them which are negative to other vendors, or make clear any comparisons are yours and not ours. Just to keep friendly relationships with our with our colleagues at other organizations. Today we will be going into how to optimize and profile AI applications, and this is a lot of new material, and I'm really happy to have a couple of our key collaborators that have gone to extra effort to create these materials. So we will have Samuel Antao coming up next, and Sadafa has been working on a very deep dive into optimization of an AI application. And of course, we have the wonderful Giacomo, who I think has got coffee this morning, so he should be almost understandable today. Anyway, please continue comments in the Discord chat. We did have the system go down last night. Would have been in the middle of the night for most of you, but it's back up, and I believe it's working fine. I'm afraid to log in and check, to tell you the truth. Anyway, I'm going to pass this over to Samuel Antao. He is our Center of Excellence representative for the Lumi Consortium up in Finland, and they've been doing some incredible work, and he has a lot of special scripts and containers for that system, so we're really eager to hear from him today. So with that, Samuel.
All right, so as Job said today, I would like to give you a bit more pointers into optimization and profiling. So in this presentation, I'll try to combine the two things, and also give you a bit of some considerations when it comes to scaling your training. When you want to start using more GPUs and what effect that might have. And without further ado, so this is the first four things I want to say here. One is this understanding that AI itself is a challenging workload, right? So it really is demanding for the computing hardware you have, and these are machines that have a lot of parties interested in using them. So it's good for you to try to get your results as quickly as possible. So optimize your application is a good idea, but also depending on your concerns, if it's just a matter of economic or even environmental, it's good to make use of these resources wisely, so you don't use more than what you need to get to the goals or to the science that you need to make. Then the other thing I want to point out is typically when you work on AI, you tend to work in fairly high abstraction, so you kind of feel that you're pretty much far from the silicon, which had some challenges in understanding what application needs for you to get optimized. But luckily there'll be some profiling tools to help you at this in this quest, and they'll be focusing on these different levels that I'll try to describe in this presentation. Okay, So AI model optimization, I think today we'll be focusing mostly on PyTorch. I think the exercise we'll be doing later today will be around PyTorch, but all these ideas can be applied to other frameworks like TensorFlow, like JAX, and they typically fall into these 4 categories. So the first is system specific. So it requires you to understand what your system is so you can optimize for it. And it typically has to do with what you call affinity, which is basically making sure that your compute is running where you expect to be and close to the other things that it needs to communicate to. So that's affinity. Then also tunables in your environment, things that have to do with communication as well, different ways to do communication, different algorithms to do your communication. Your libraries may also take different tunables. Depending on what you want to do, or maybe there is some logging you want to get out of it, so it also informs a bit your optimization effort. And then there are the frameworks, so they also have their own techniques to optimize the codes. Kernel fusion is possibly one of the main optimizations that goes into frameworks like PyTorch, but there's also Triton that tends to give you a bit of some solutions to be able to almost have native performance for Python code in memory optimizations that you can do as well to make sure the what it lives on GPU is big enough for you to actually do and use the full power of that resource. And then there are the things that actually fall a bit more into the AI engineer job, which is the batch size optimization and also the strategies around parallelism. And the model parallelism could be data tensor or the pipeline. So this is the 4 things that kind of matter here. So I'll try first with the affinity part of it, and to understand this, it's typically useful to discuss a bit device visibility. So when you run your workload on the machines that you have available to this course, there are many GPUs there, right? And there are different ways for you to control the visibility so that your, say, PyTorch instance picks the GPU you expect to pick. And typically, the visibility is controlled at the environment level. There's these 2 environment variables called heap visible devices, and basically you just provide a list of the GPUs that you want your PyTorch instance to use, and with this you can just this will return 4 if you run this, because you have 4 devices here. But then there's also a lower level, so the ROCm runtime, so it's kind of a lower level runtime where IP is implemented upon, and for that to limit visibility at that level, then you have these Rocker visible devices. My recommendation is to use the first one, because all these AI frameworks tend to be implemented on top of HIP. So you don't need to be limiting the visibility at the ROCm runtime level, which will also preclude some opportunities in optimized communication across devices. So stick with this one if you can. But there's also other considerations to have here. That sometimes not only the environment can be used to specify visibility, there are other things. Can be an argument that your script takes. Right? If you go to the internet and get a script that does some distributed training, you may have an argument to decide which GPUs to use. Or it can be something that is based on how you are running your script. It could be if you're using MPI to start things. It could be the rank of your process that can be used to decide which is the GPU. Could be the CPUs that are part of your allocation that may be decided, or it can be, whatever auto functionality in your script that auto determines this sort of things. Typically on PyTorch, my experience is that the local rank, so basically your process number 0 takes GPU 0, process number 1 takes GPU 1, and so on and so forth, tends to be the case. But don't forget that this may not be general enough for other things. So just bear in mind this can be something you need to control. Okay. The other bit of affinity, and here I'm basically picking up on a MI3 and A node that you actually have available for in this training. So you typically have in this case for GPUs, and they have these red links here that basically are connections between them. Right? So basically data can flow between these 3 different devices, but in this case, each one of these chips is actually going to have CPUs and GPUs inside this chip, right? And so if I try to zoom into what is going on in one of these chips, and this is kind of what I have here in this image here, you typically have the CPU bit of the chip, and you have the GPU part of the chip, and you can just imagine, and you have of course 4 of these, as I was showing in the past picture, and you have 2 options here. So you can have your CPU actually communicate directly to the GPUs in the same chip, or it can go across chips. And you can just imagine that this bit is far more efficient than this. So you really want to have some control on what is running on your CPUs and which GPUs a given CPU is working with, so that you use this route more than this. And the 2 tools that or commands that are typically useful for you to work around this is this ls CPU and this ROCm SMI show topology. The first one gives you an idea on how CPUs are distributed by what we call non-unified memory address domains. So this is the NUMA acronym here. And here I know that NUMA node 0 will be CPU 0 to 23. NUMA 1 will be CPUs 24 to 47. And if I go to this ROCm SMI show topology, I can also know which GPUs are part of which NUMA domain. And basically, the exercise is to match one to the other. So I know these are the cores, CPU cores, that I want to be using with this GPU. So basically, it's all about combining the information from one to the other and just have this map and make sure you observe this map and how you do it. There are multiple ways. NUMA CTL is a command that you can use. It has this argument that allows you to select which CPUs you want to be using. MPI has its own binding arguments as well to select which CPUs to use, or your scheduler can help you in this, in this regard. They have options like GPU bind closest, so that for a given allocation, it also makes the GPUs available that are closest to the cores that are part of that allocation, right? And this can make a big difference, in particular, if you are loading a lot of data into your GPU. So basically, you will want to be using this link much more than this one. The other bit that is important, in particular, if you go, look at the other sites, like Lumi, like Frontier, they have highly optimized network implementations, things like Slingshot, and this implementation has its own ways to do things like collectives more efficient, right? And typically, when you are doing AI, a library that is going to enable you to do this communication is the RCL library, which stands for the RCCL library. So if you use NCCL, it's kind of the equivalent to that. And this library basically is used because they allow you to orchestrate a bit better the communication with the other compute that happens during the AI training and inference. Is when you are using this optimized network implementations, there are things like the CXI plugin, which is a piece of software that allows RCL to be bridged with the provider of this network and enjoy all the niceties that this network implementation provides, right? So this is something quite important for you to get a good performance in your communication. And good performance here means 3 to 4 times faster collectives comparison to not using it. So this really makes a big difference. So I typically recommend to always take a look that you are using this plugin. This is how you can see that if you're picking up a plugin, if you are using an HP system or something that has a specialized network implementation, you can check that is picking up the plugin like this. Just a warning that sometimes, in particular around AI, people just get a container from Docker Hub, they go run in the system, and that may not have this plugin available, right? So check with your site to make sure they have specialized containers for you to use that take full advantage of the network, because it's really, really a big difference. Now, complementing this information, there are other tunables here that you might be interested in using around RCL. One has to do with the network interfaces. I mean, you may have nodes They have many different interfaces, so it's typically a good idea to select the ones that matter. Typically, if you're using Slickshot, like the MI300A node that you have, even though you have the provider there, but if you go to Lumi or the HOS system, so this is typically what you want to use. A high-speed interface is available, so that RCL doesn't bother try to communicate through other interfaces the node may have, say, for admin work or things like this. The other bit that is important to mention here is the enabling RDMA, so remote direct memory access is basically the ability for one GPU to send data directly to memory that lives in a GPU on a different node. And this is enabled by this environment variable here. And typically you don't need to worry about this if you are using a recent ROCm, like the one that is available on the systems you have here. But if you're going to more legacy ROCm installations, this might, this is still required for you to enable RDMA. And this, this plot here, I think this was already shown to you in the first day, but I just wanted to really stress how important this is. This shows you, how important it is to get things right. So this is the baseline. If you don't use plugin, if you use RDMA, this is if you use the plugin, and this if you use the plugin and RDMA. And you can see from here to here is like 10x, and you can just imagine how much farther you can scale your work by having much more performant communication. Again, careful with external containers. Don't assume anything. Just make sure they actually have plugin available, and the environment is set right for you to be working here as opposed to be working here. Okay, so moving on to the environment settings. There are many, environment variables that you can use. There is no way I can be exhaustive about this. So I just wanted to point here, documentation is your friend if you really interested in understanding all the tunables. This is the link for you to go investigate what are all the options. For PyTorch in particular, the one that I would like to put it out there, because this is quite important in a way that allow you the implementation to tune itself to the memory, the matrix multiplication sizes that your model requires, is this PyTorch tunable up_enable equal 1. And this makes PyTorch to do a tunable step prior to actually do your training and have optimized gems to use disposal during the training. There are other things that I want to mention here, and this sometimes can be a bit tricky, not because of performance, but also because it may actually clash with your file system. So if you go in most sites, your home folder, which sometimes the default for certain things, is not a high performance file system, right? And things like MIOpen, which is a library that gives you several AI primitives around things like the convolution kernels and things of this sort, very useful for computer vision and other things. It tends to do some just-in-time compilation when you run it, and it goes into a cache. Right, there are these two environment variables that you can use to decide this cache to live somewhere else out of your home folder, because all these databases that are generated of this just-in-time compilation, don't have to, don't have to clash with the limitations of your file system, and particularly if you're using, say, 1,000 process doing the same thing at the same time. Right. So if you are using multiple ones, you may want to have the cache dependent on a node ID. Can do something like this, and with this you can spread a load and have those many locks coming into the same place, which might result into hangs. The other kind of optimization that these frameworks provide is this kernel fusion, and if you look at the kind of compute that your AI workflow does, this consists of many kernels running back to back, right? And the thing is, the moment your GPU activity starts to be the same order of the latency that it takes to start that same work, then you start having gaps, and that's what I'm trying to show you here. So in this line here, you have the runtime activity that actually spins some work into the GPU. And the moment this box here starts to be in the same order of magnitude as this link here, then you start having this gap. So the solution to eliminate this is try to have a single kernel that combines this sequence of kernels. So they have a single launch to do, multiple things. And this is automatic fusion is something that Torch comes with, so you can enjoy it out of the box. Typically does sensible options when it comes to that. But you could also go the extra mile and just implement your own functions with your own operator and use these decorators to basically instruct Torch, hey, I want to compile a version of this operator right here. So it's a way for you to also fuse things together. Other things that have to do with framework optimization is Triton. So Triton is basically Python code that you can compile to the GPU, and it consists of a domain-specific language that is provided by this module right here. And the kernels, if you are familiar with writing HIP or writing CUDA, this will look, this model looks quite familiar, where you have basic a load and a store. In this case is a vector add, and you have some logic to control how you access this array based on the number of threads, the block size that you have in your kernel. So this is the Triton way to do things from Python and enjoy kind of native performance out of your GPU. There is ahead of time Triton, and this is basically a collection of kernels that were written on Triton that are available for your implementation, and this typically target the attention layers of your model. So that is the optimized flash attention implementations based on AO Triton. So this collection of kernels that is installed alongside PyTorch if you install it from the ROCm repositories. The other bit I want to mention here is composable kernel. Is another project that you can find on a ROCm GitHub, and this is also a way to give you optimized ML primitives. It provides you like a tile. It comes with its own programming model, which is tile based, and the idea is to allow developers to interact at different levels depending on their abilities and their confidence in changing things. So maybe just API level, maybe just the way you instantiate the kernels, or you can go all the way down if you really know how to tune gems and reduction operations and things of this sort. The good news is that most of the time PyTorch makes use of this out of the box for you. You might not have to worry this, but if you really care about performance, is useful for you to know how that this exists, and this is where all these implementations that your PyTorch run are coming from. Okay, so the next thing here is parallelism, and I think I'm going a bit late here, so I need to speed up. So you have multiple GPUs in your system. So now the next thing to do here is to understand what is the parallelization strategy, right? And typically you have mainly two of them. One is if the model fits on a GPU, which is the data parallelism, when you have the same model running on different GPUs and you fit it different data, and then you compute the losses, or you do a reduction of the losses and communicate the gradients back. That's one approach. But if your model gets too big, then you may have to do something like this. You have to partition your model into two GPUs and have this sort of pipeline approach, or where one mini batch is already in part C and D. The other one is still in part A and B, and then you have again the loss computed together and gradients communicated back. And you can imagine this has different profiling characteristics. So this one is balanced because all GPUs are doing the same thing. This one is not, right? So the GPU 0 and GPU 1 are doing different things, and this has implications on how you're going to optimize things, because you need to look at the GPU that is doing the thing that you care about. Just very quickly, this slide here is a bit more, I guess, documentation if you want to refer to it later. Ways to do this, partitioning is one of the typical ways. This FSDP stands for fully sharded data parallel, which is a way for you to create shards of your model and have them distributed across GPUs. And it comes with some nice ideas on how to hide communication latency with compute. And you can have a look into the API. It's typically fairly easy to actually get enabled to use things like FSDP, because they follow the same idea that you have on PyTorch of having the wrapping of a model with this fully sharded data parallel object and it gives you an instance of the model that is enabled for that. And the other good news here is that if you go to accelerate, like frameworks from Hugging Face, there's like a nice example on how to use FSDP with transformers. This is already enabled there. It's just a matter of setting up a flag or setting an argument that you can just have FSDP enabled for your framework. Deep speed is another thing that another framework that I tend to see quite frequently on Lumi machines. That comes with like optimized set of distributed operations that you can enable. So by setting them to 1 when you install it, this is kind of how you could install it. And there is this nice utility that tells you which ones are available. So, and actually has the ability to just in time build these operations. But if you are doing things in a distributed way, it's always a good idea just to install the operations you need in advance, so that you don't have, say, 100 ranks, building the same thing, right? So this is a good idea to do, the installation in advance, setting up the operations that you actually care about. Okay. So some scaling implications that I wanted just to stress here. Typically you want to train faster, and what do you want to train bigger? When your model just doesn't fit on GPU, this is how you want to scale. But there's always so far you can go, and it really depends on your model and the different bottlenecks. But typically the workflow is what I'm showing you here, where it starts from you having a single node performing the way you expect to be, then you scale multiple nodes, you'll see the batch size decreasing per GPU when you start scaling, and then you need to start worrying about this sort of things. If basically you can fit enough data into your model and you are not bound by I/O, if your communication doesn't start dominating, or if you have basically by distributing your loss just converges slower, right, for the same accuracy. So this is something that you always need to be thinking about, not in an isolated way, but in an holistic way. Just look at all variables, because they can, really, influence what you care about, which is running your model faster. So there's no point in having a kernel running faster if your model overall doesn't train faster. And this is what I have here on the slide, just to stress this. The goal is to train faster. And I have like a couple of examples here, that sometimes the bottleneck might not be on the GPU, right? It might be elsewhere. It might be in this case, you have, this is kind of the GPU activity, and this is the communication that completely dominates your recall kernels, that completely dominates your profile. Or you can have something like this with very little GPU activity, and you have the fetching of the data taking a long time. So you need to look at all these things holistically so that you optimize everything together. And this is the challenge that typically AI applications have. Okay. And now just trying to go over the tools. I mean, this is going to be the examples you're going to have in the next presentation. Will be covering this with a bit more detail, just a bit of an overview of the different tools that you have available. From the framework level tools, PyTorch has its own profiler module that you can use. Deep speed, the same. Triton has its own profiler as well. And then you have the tools that AMD provides, which are not AI specific, but they apply to AI as they will apply for to any other kind of HPC workload, like ROCm SMI that gives you the driver information, and then the different ways to select system level performance with ROCprof and ROCprof sys, and also the kernel details. So basically how well your kernels are actually using the resources on the GPU. This is ROCprof compute that basically augments the information from the counters that ROCprof provides. And just a bit of more detail here. So the PyTorch profiler typically you use to define a range in your code that you want to collect information, and you just define this torch profiler profile object, and you start a profiling on that specific context. And the result is a trace that you can even load on TensorBoard or in this Perfecto tool, or just look at a summary that is presented as tables and gives you a lot of information about execution time, memory count, the shapes. Deep speed as also the profiler that you can use as a wrapper to your model, or you can also directly specify it in your deep speed configuration file, and this gives you some information about how far you are from your attainable performance. It gives you the performance of the different layers of your model, so this is quite useful information. And then Proton, if you are writing Triton kernels and you know how better, to know about the improvements you are making in your code, this is a good profiler for you to use that also works by wrapping the execution of your kernel into this testing object that Triton provides. Then the other system level tools, ROCm SMI is a very nice way for you to very quickly understand if the GPUs are used in a balanced way, if you are using the memory that you're expecting to be using. And then there's ROCprof sys that basically complements the GPU activity with a CPU activity. And this is the way you'll be using it. You record a session for your Python script. It has this double dash syntax here to distinguish what is arguments from ROCprof sys to your own application. And then you have a nice timeline that you can visualize when you can see side by side your GPU activity and your CPU activity. And this is pretty good to see things like I was showing you before, like the IO bottlenecks and when that things synchronize. Then the things that gives you more kernel level information, ROCprof v3. So this can collect you a lot of counters, and you can try to and statistics on your kernel, so you can see which one dominates, and so you can focus a bit more your execution. And then ROCprof compute just basically gets all these counters that ROCprof can collect and try to help you interpret them by organizing all this information in a more human consumable way. And where you can target specific analysis like the roofline that also allow you to understand how far you are from an attainable performance for a given device. So this is like the tools. And finally, just to close very quickly a bit, the workflow that typically tends to be followed in this case. I think the starting point for everyone, particularly if you are using PyTorch, and because you typically are comfortable writing Python code around your model, you might not be very comfortable, with other tools. So basically, you can do PyTorch profiler all in Python and control everything from a place where you are comfortable with. So this would be my main suggestion when you try. So to identify what are the hot parts of your code, right? The moment you know this, then you can go on to the next step and then use ROCprof compute to really do an analysis of the kernels or the bits or the operator that is problematic, understand how you can improve the performance, if you can just do more, if there is fusion opportunities, if there is ways to improve your memory access patterns. And then if there is also the question if you're optimizing what already is there, or if you want to write your own custom kernel. So in that case, you might be willing to use Triton. So then this framework specific profilers starts to be a good way for you to complement what you get from ROCprof compute. And then at the end, depending on your maturity of your workflow, you may be interested in develop your own regression tests and performance tests to calibrate your own expectations on performance, so that you make sure that in a month when you revisit the implementation, you did something that is not a regression for the code that you already had. And this is what I had for you today. A disclaimer here, because I have to. And I think I'll monitor Discord to see if there are any other questions. And I'm sorry that I'm probably a bit over time.
Some really good stuff, Samuel. It always amazes me how much work you've done at UMI to get things optimized. And it does take extra effort.
Oh, thank you. Is there any questions that we want to address now, or we go to the chat directly, I guess?
Okay. So there's a question here from Mark saying he did not fully understand the difference, what you get from ROCprof v3 and ROCm systems. Mm-hmm. And I think that's really our next presentation.
Right.
So
yeah, I didn't
give a brief answer.
Yeah, I didn't elaborate much of that exactly because I know there's going to be addressed later. But the idea of ROCprof sys is just to complement the information on a GPU to what happens on a CPU. So on RockProf, you can understand the GPU kernels when they are launched, but you don't know what your CPU is doing. So basically, in one place in the code was a specific kernel launched, for instance. Or if there is some specific I/O bit that is computed on a CPU. So this is what the extra information that RockProfsys can provide you.
And we have a couple threads in here wondering why the set of flags isn't just the default. And I think also you might address why CXI slingshot is not the default. And the complexity there, and also why, if you got a generic wheel, you can't put that in, any of this in. Yeah. Go ahead.
Yeah. So that's the thing. Like RICL, the communication library, has to work on many different systems, right? There is from InfiniBand to Slingshot to others. So basically, this is it has its generic implementation, and then as a set of tunables, they are really dependent on your system, right? And Slingshot is, I guess, one of the main variants you can find with the AMD GPUs, and that's why this is so important to get good performance. So this plugin is kind of a result of work that we do closely with in this case HPE, to actually make good use of their network provider, right? So basically, this is an interface between software that two different vendors develop, right? And it's important for you to really understand what are the requirements there. But typically, the different sites try to do a good job in documenting this and providing a set of containers, probably not wheel files, but containers at least, that has all these different bits installed for you to enjoy, without having to run into these issues are not just using the right provider. Any more questions?
Yeah, there's a short. Go ahead, Chuck.
Go ahead. Oh no, I was gonna mention a question about running Torch Titan on Lumi. Gaurav says, "Hi Samuel, thanks for the great presentation. I'm trying to run Torch Titan in Lumi with my own implementation, but the container I'm using doesn't have the tuner you mentioned. What would be the best way to use it?"
Well, I guess I'll try to maybe respond on a chat. I think that's easier. I can give you a few pointers on how to build. It's actually not difficult. But the other option is to mount it from the host. So when you use containers, there are installations of the plugin that you can leverage. But I can give you a few pointers, and I think it's just easier if I just type it down on a chat to give you this, tell you where this code lives.
I also want to mention while we're at it that there's a lot of tuning going on by the libraries team and the framework, the AI frameworks to optimize these things. And every release of ROCm, the performance improves a little bit. So trying to stay up with the current version, it can have a big effect. It's a little more difficult when we're on big HPC centers. They often don't move forward as quick as any of us would like, except that we don't really like them to move forward because they take the system down for a couple of weeks. But Samuel, you have provided newer ROCm modules on the system to help with that. You want to talk a little bit about that?
Yeah, so that's one of the, there are limitations. So one thing we cannot control is the driver that lives on a system. So this is something we cannot control. What we can try to do is to provide modules in an environment that allow you to do the latest ROCm that we know works with the driver, and also sometimes works well with the communication layers that are available on the system, like MPI, because there's other constraints that you have. But yeah, we typically have the modules that we can have this environment that just looks for a snapshot of a given ROCm instance, because ROCm has this user level that can be installable pretty much everywhere. Even you can do it if you really want to spend the time doing it, or use the containers. And this is typically more useful on AI, because we already have a lot of PyTorch or Python stuff already installed there, which also helps the file system to cope, because you can imagine that you use thousands of nodes and each one is loading thousands of Python files at the same time. The experience for all the users is going to be very low. So that's why for AI we tend to prefer containers, or Python workflows in general. We tend to use containers, but for everything else we have these modules that you can just compile with the compilers that are specifying that environment, and you should be in a good place.
Yeah, even here on our training system here, if we had everybody go in and download wheels, nobody could get any work done, especially if you got 30 people doing all the same download. So it depends on where you are and in your environment, what the best approach is, but you should consider that. We have a question here from Adam. What other fabrics are supported besides HPE Slingshot, and what are the corresponding tunables? Now, I want to point out that Slingshot is an HPE product, not an AMD product.
Mm-hmm. That's correct. And so there's, I think the main ones is InfiniBand and Slingshot. I think there are other providers. I mean, if you go to Amazon, for instance, they have their own network, and the tunable is very similar, though they may eventually provide you the specialized plugin for that. But the idea is very similar to what I presented to you here. I mean, it might be others. I mean, I may not have an exhaustive list, but it's typically InfiniBand, which is something you get by default from RICL, because it's already native, support from that, and RICL works pretty well with that too. But for Slingshot, there is what they call this libfabric provider, which is kind of a standard, and a lot of people that develop their own networks adopt this standard. So that's why these ideas of using this tunable for Slingshot could apply for any other network provider that uses libfabric. They'll be providing you a plugin, like the one I mentioned here.
So I'm going to add a little bit here, and Samuel can correct me if any misstatements I make here, but there are actually a couple different communication layers within the node. If we have a 4-socket system with 4 MI300As like we do on the Perry Peak air-cooled that you're using, there's infinity fabric between the GPUs. So you've got one level, a very fast level there, but then you got to connect between those MI300As, and that's going to be local to the system. And we don't have a really high performance network on these nodes because they're really meant for testing. So check with your site what they're using for their communication layer and what their recommendations are. I mean, it may take some digging, especially if you're at a local university site where they don't have a lot of information. They don't know much either. So go ahead. Anything to add, Samuel?
Yeah, I mean, this concerns is about getting out of the node, right? So if you have RICL, regardless of where you are, if you are just looking into single node performance, you should be in a good place without having to worry about these plugins, right? But yeah, so the Infinity Fabric support comes directly from RICL, right? So this is basically what he uses, right? It's just this extra bit that, as Bob was saying, that has to go across node. I think in these nodes, you don't have the provider installed. I think even if you wanted to use the plugin, you don't have the provider there because, as Bob said, it was not the goal here. But it's important for you to be aware of these things, because the moment you go to Lumi or other sites, this is, I mean, 10x difference in communication performance, is day and night, right? So it's really something that you should be aware of.
And we also have on a lot of our sites, for example, on the HPE sites, you usually have a Cray MPitch for the MPI communication, but some of them have a custom open MPI, and other sites like what we have up on your training system here is open MPI. So this is one of the difficulties. How do we deliver any software dependent on MPI when there's a variety of MPIs that might be on the system and maybe custom. And so when we build this module that you're using for PyTorch, we add all the PyTorch friends in there. So there's flash attention and composable kernels. But we also compile from source so that we can include the GPU-aware MPI. And we also compile only for the GFX models on the system. And it takes 6 hours to compile the thing. I mean, it's not a trivial process, but the end result is really good for the users of the system. Now, if you're the only user, it's probably not worth doing that. Okay. Do you want to summarize, pick some of these other? I see Samuel's on the chat now.
Yeah, I was yeah.
Go ahead.
Yeah, I mean, I was just, I guess maybe I can just go to the chat and respond to the specific things. So there was questions about, can you do combined tensor parallel with, yes, you can do 4 tensor parallel with 4, you know, whatever makes sense. But again, don't forget the goal is for you to train faster. You know, that's quite of the, because sometimes people may get too distracted and just try to just parallelize more. But don't forget that, you know, sometimes when you parallelize more, each instance of your model learns different things, right? So your loss may be coming down a bit slower. So it's always, you know, an exploration that you need to do. And but yeah, this, you know, types of parallelism should work for you, you know, with no problem.
Okay, we've gone a little bit longer than we planned, but this was really, really useful discussion and presentation. Let's go ahead and take the chat to the chat, and let's let Luka start his presentation on PyTorch profiling on the AMD GPUs. And we'll probably shorten the exercises and break a little bit. I just think this is too valuable to cut it short. So, Luka, are you on the system? Ah, there he is. Okay, Luka, are you all ready?
Yeah, can you hear me?
Sound check good. Yeah.
Okay, let me
go ahead and share some slides.
share.
And I'm going to introduce Luka while he's getting ready here. Luka is our representative at the Max Planck Computing and Data Facility in Munich. And he's been working a lot on the profilers, testing them, finding bugs, cleaning them up, and helping the development team identify the issues. And that's a big challenge because these are interactive tools. And so it takes a lot of pointing and clicking and testing to get these to work in all different environments. So with that, Luka, take it away.
Thanks for the intro, Bob. So, and thanks, Sam, for the nice presentation in the beginning. It gives me a really nice, I think, background and context for everyone. So my presentation today will be kind of a deeper dive into the tools, some of the tools that can be used for profiling PyTorch applications, and we'll look at a couple of those tools through an example. So basically my talk today will be focusing first to provide you just some overview and examples. And then I will talk about first the PyTorch profiler, which comes together with the PyTorch installation itself. It's a built-in profiler. And then I will talk about 3 AMD profilers: RockProf V3, RockProf Sys, and RockProf Compute. So why is application profiling important? Well, AI applications are really kind of this complex multi-layer structure that really complicates profiling and understanding performance in general for the applications. And I mean, one can profile at very, very different levels. So first there is the Python profiling on a Python top level, let's say. Then one can look at the underlying libraries in C, C++, Fortran. Look at some of the most important kernels like GEMS. Then communication both on the node and across the nodes. memory requirements, but also very often in AI cases, the I/O can be the bottleneck. So this is something also to verify. And the thing is that different parts of an AI application always require different tools to understand and analyze this performance, and later, as a next step, optimize it. So profiling tools that I will present today, and this is not an exhaustive list. I mean, Sam already mentioned a couple of others, but we decided to focus on these ones, and starting from kind of a top-down approach from the simplest ones, the ones that are closest to the application, which is PyTorch. And as mentioned, this is a built-in profiler to the PyTorch, and it has the operator level performance analysis, and it does work on AMD MH100 A's and X's. And then the next simplest tool would be the RockProf v3 coming from the AMD, which is the tool which is collecting data from hardware counters on AMD GPUs. So this tool can display kernel runtimes and timelines for different operations running on GPUs. And then as an upgrade on top of the RockProf v3, one can look at it that way, would be the ROCm system profiler, which is timeline trace, which allows the timeline trace collection for both GPU and CPU activity and many other things. So one way to look at the ROCm system profiler, it's kind of on top of the RockProf v3. And then finally, the last tool, which is probably the most advanced, especially in the AI context, would be the ROCm compute profiler. So because this one is really focusing in detail on the GPU kernel performance analysis. So with this tool, one can profile and analyze different performance metrics of individual kernels running on GPUs. So to present these tools, we have picked up a very simple example, the Cypher 100, which in its basics, the core of the code is presented here in these lines. I will not go into detail because actually the example of the whole Python script, which is, by the way, not that big, is in the usual HPC training examples folder in the ML examples and the PyTorch profiling. So there you can see the train profile script in more detail. So basically, this repository will contain a README, which can guide you through the exercises, the main script, which is running the training, then a couple of utility scripts, so one for downloading the data and another one for setting up the environment, basically loading ROCm and PyTorch modules. And then there are 5 exercises inside those directories, each one with its own READMEs. So first one without profiling, and then by using 4 of these profilers. But basically, each one of these directories contains kind of a helper bash scripts, which are then underneath calling the train Cypher 100 Python script. So you can use the helper script, or you can develop your own as you wish. Note that some of these scripts are, I would say, tested more than others because basically, especially for the ones related to Slurm, it's very hard to make these scripts, helper scripts, very general. So look at the things that if there's some trivial things that need to be changed there for your setup. So the main script is this train Cypher, and it comes with a couple of options. So first one can select where the data is stored, and then or to download it, not download it. But then there are also a couple of things that one can test. For example, different batch sizes, precisions, max epochs and steps. And actually one can enable Torch Profiler through this script. And then one can also select a model. So this example is supposed to represent kind of a typical workflow for the AI apps and typical parameters that with which one can play with when trying to optimize, at least on a higher level, the application performance. So regarding the setup, well, the most important for these exercises would be to set up this first variable. So to put this profiler top dir to the main directory, because this is the variable which will be used by all helper scripts later on, and it will search for the train script based on this path. And then there are a couple of other variables which are actually set inside your helper script, so you can check them, or you can set them by yourself if you are writing the tests and testing on your own. So first ones are related to the addresses and ports especially regarding the executions on using multiple processes. Second one also is regarding the MPI, so setting the MPI ranks and size. Finally, if you're using Slurm, don't forget to set some of the Slurm variables. And then finally, environment variables needed here are ROCm and PyTorch. Note that actually on AEC6 at the moment, when you load the PyTorch module, it will automatically also load OpenMPI module, which is necessary in case you want to run on the execution on with multiple processes. So there is also a helper script called download data, which basically again calls this main train cipher script with the -- download only, which will basically just download the data. I think something a bit less than 200 megabytes, on which the model will be later trained. So to run the example, you can either look at these bash scripts or do it yourself, just Python and then train cipher. If you don't specify any arguments, it will use the defaults, or you can also play with different arguments. So the expected output of this execution is listed here. So basically, it will tell you it will run for 20 steps, and I think the most important number for us regarding the performance would be the one at the very end of each row, which is basically the performance, the images per second per GPU here. So note that this is per GPU, so these things have an impact, especially if you're running with multiple MPI ranks. This selected example, Cypher 100, is not performing well at all. I mean, it was on purpose that we selected a very simple example just to show the profiling, because the focus of these presentations are the profilers, not the performance. You can check how to improve those, but basically the idea here is that you see how the tools work in practice, and then that you apply them to some of your own problems or to some of the other examples that were discussed previously this week. So first, what you can do is, what you should do actually before any profiling is to establish the baseline. So, and that is why here we have the first folder, the no profiling folder, where the idea is that you just basically run first the serial using a single process, and then the parallel execution with multiple MPI ranks. And for this, please make sure that you allocated either the whole node or a sufficient number of GPUs on a node if you're running MPI. And then to see if everything is working fine and what is the baseline performance, what are the numbers, what are those numbers here of the images per second per GPU, because this will be your initial and main performance matrix. While running these examples, you can also check if the GPU is used at all. I mean, one way to check it is to look at the performance, but as Sam said, don't trust anything. You always verify. So one way to verify that your code is really running on GPUs, the simplest way is either to check with ROCm SMI while the code is running, or to enable AMD log level and just to see if there is any GPU activity at all. When running this benchmarks without profiling, the idea here would also be to inspect the scaling efficiency. So comparing single process executions to the multi-process executions. And this is also something that you can do later on when the profiling is enabled as well. And also another thing that you could do is to modify the arguments of this train cipher 100 script, like batch size or precision, and see what is the impact of performance when you're doing that. So with that, now let's move on the first profiler, and here we will start with the PyTorch profiler, because this is the profiler which works on the operator level. So as mentioned, this is the profiler which is often the most easy one to use for the users of AI applications, because they're used to Python, they're used to PyTorch. And actually, they can, since this is a built-in profiler that comes with PyTorch, it's always there if you're using PyTorch. And the way to use this profiler is to actually, one needs to change the code. So here I'm just showing some short snippets for the whole thing. I encourage you to look at the whole train cipher script. But basically, the idea is that first, in the initialization of your training, you add something like this, so that you enable the PyTorch profiler and create this profiling context. Then inside your training loop, you're using the context, and you typically want to do that only on a single MPI rank, even when you're running multiple processes. And then finally, in the finalization, you will make sure that the trace you're collected is then exported, in this case, to the JSON file. For more documentation, please check the official PyTorch profiler recipes listed here with this link. And note that for just this training here, in our training cipher 100 script, where we already put the PyTorch profiler, and you can actually enable it with the argument of the script, which we called torch profile. But this is really specific to this script. This is not something that it's not like in your script it's sufficient to add dash torch profile and it will provide something. No, you first need to put these things, this instrumentation, in your code, and then also enable the torch profiler if you want to see the outputs. And by the way, in the torch profiler exercise, this is already enabled by default. So you can if you use the helper scripts, the bash scripts, you will already see some output. So one way to test this would be to enter the torch profiler directory and then just run single process. This should work fine on ASC6. And basically, at the end of the execution, you will see a profiling summary by a PyTorch profiler. So basically, here you would see the most important functions and how much time did they spend on a CPU, how much time did they spend on a GPU. In this case, it will be written CUDA, but I mean this applies to both AMD and NVIDIA GPUs, just called CUDA here. And there you can already see if something is running on your GPUs, what is running on your GPUs, and how much time does it take compared to the rest of the execution. In this case, as mentioned, this example is performing very poorly. I mean, it has big initialization, and then we also don't run it for a long time, so there is not that much GPU activity. But for others, hopefully, for your examples, hopefully this will work better. To analyze this in more detail, what you can additionally do is the JSON file which is generated, you should copy it probably to your laptop with SCP from ASC6. And then you can open this JSON timeline profile using the Perfetto tool. So the Perfetto tool is just the UI actually developed by Google, and you just open the browser. Typically, we recommend Chrome. Connect to this URL and open the downloaded trace profile. And the output which you should see should look something like this. So basically, this is the typical timeline where on the x-axis you have the time, on the y-axis you have different resources, different things to see, and then here you can see for different threads you can see different activities. So for example, we see that we are profiling the steps 9, 10, 11 here, and then for each one of them you can see the function calls and what was happening in the application while it was running. So here we can see the timeline on the top. By the way, one of the big advantages of the instrumentation, in this case using the PyTorch profiler, is that you can really select what you want to profile, which part of your application you want to profile, and also when. So for example, in this case, we selected that we want to profile only steps 10, 9, 11, 9, 10, 11, and not the whole execution, just to make the profiling smaller and easier to digest. I mean, in typical cases, you want to skip the first one or two warm-up steps and only then profile, and then disable the profiling in case your application is running longer, just to make sure that your output traces are not too big. Okay, so now after this, let's move to the AMD tools for running PyTorch applications. So here I just group them in this way. So on the very bottom, we have the lib rock profiler SDK library. So this is the tool which is actually used for tracing and profiling and provides the infrastructure. This is the, oh, okay, I guess, So I'm still sharing the screen, but you lost my presentation, right?
You are in presenter mode, but yes, we can see it.
Yeah. So
there we go.
So there we go. Yeah. So the PowerPoint decided to restart on me.
It did that to me
Yeah.
3 or 4 times last week.
I'm lucky I heard that from you last time, because I would have panicked now, but okay, thanks. I know this happened to you. Okay, so if it happens again, I will open a PDF. So basically, on top of this lib rock profiler SDK, we have rockprof v3 and rockprof sys tools, which are relying on this library. And then on top of that, rockprof compute. So let me start with rockprof v3. This one is probably the simplest one, and it's the tool for GPU tracing and counter collection. So this is really a tool for profiling basic AMD GPU activity. It was introduced in ROCm 6.2, and it's the successor of the rockprof and rockprof v2 tools. And its main capabilities is to profile the GPU hotspots, so to identify performance bottlenecks. Also to visualize some activity on the device, so HIP, but also HSA, the GPU kernels, data transfers, and so on. And also the performance counter collection, so to analyze the kernel performance in more details. There is support for Python, which is what we are mostly interested in now, but also for other things like OpenMP. And for the documentation with more details, here is the link. So let's see how to use rockprof v3. So basically, I mean, you can search for the documentation for more details, but the simplest way to use it is to specify rockprof v3 and then say what kind of things you want to collect. In this case, we say we want to collect kernel traces, so the information about the GPU kernels, and we also want to provide statistics, so some summary of this. So that's why we combine this stats and kernel. And then later, very important thing that I myself also very often forget is to add dash to just split this from the rest. And then after it, you put Python and the application with your arguments, or if it's not a Python application, then you just put your application here with the arguments and so on. So by default, this will create the CSV output files on the ASC6. However, note that starting from the more recent ROCm versions and probably in the future, the default output format might change. So you actually, if you want to get the CSVs, you need to additionally specify that the output format here that you want to see is the CSV. With running rockprof --help, you should be able to see all the available options, or you can check the documentation. It's very nicely described. So in our examples here from the repository, to run this, what you basically need to do is to enter the rockprof v3 directory, and then either you run the helper script, which is called kernels.sh, and basically this bash script is just a wrapper which underneath does some preparation and setup and so on, and then finally calls rockprof v3 with --stats kernel traces, and then also just for convenience, I there specified the output directory, which you can put any name that you wish, and output file names, and here also the format CSV, just in case somebody is using the script with the newer ROCm. This should generate basically an output directory, in this case called single process, because this is the name I gave to the output directory. The next step after running rockprof v3 would be to inspect what are the files in this new directory. You can do that just simply with ls. And then what I can recommend you to start doing is to look at the summary. So summary is always called _stats.csv. And basically by just opening and looking at the first lines, you should see something like this. So it is basically a CSV with the information. Sometimes looking at the CSVs in your terminal is simple enough, and you can analyze it there. This is something that I typically do. But sometimes it's also the names of the kernels can be very long, and then the analyzing in the terminal can get a bit cumbersome. In which case, you can just download your CSV output files and open them in spreadsheet viewer like Excel or whichever other tool. It should provide you with the output similar to this one. So here we can see the most important kernel names. Why kernel names? Because before we specified here that we want kernel trace. So this will give us kernel names. If we would have specified here something else, like more information about memory transfers or something like that, then we would see memory transfers as well. In this case, only kernels. And what I typically look at first when I start is, of course, the first kernel, the most important one, and the percentage of the total executions on the GPU this one took. So in this case, it is 8-point-something%. So it is not that dominant. And as you can see here, so there are many different kernels in this specific case. And actually, each one of them with many calls. So in the second column, you can see the number of calls for each of these kernels that were executed in this execution. And as mentioned, the performance here is not dominated by a single GPU kernel. However, for your application, this may be very, very different. And sometimes it's very dominant by a single kernel. In which case, of course, with the rest of the analysis and later optimization, you really want to focus on this first one, on the first bottlenecks that you can address. So similarly, for a parallel run, again, you will get similar type of CSVs for each MPI rank. But actually now, if you look at the output, you will see something slightly different. You will see that actually much more performance of, okay, I guess my PowerPoint failed again, right? So let me then open good old PDF. That should be
good move. We're scoring is PowerPoint more reliable than our HPC system. It's a horse race.
That's dangerous territory right there, Bob.
Yeah. I must admit that this never happened to me before, but yeah, it started happening to you, Bob. So I guess this is a new trend.
The beauty of live TV.
Yeah. Okay, I have it here. Let me just open it, and let me now again share the screen. The screen pop up. You should see again now my PDF, right? And then what is the shortcut for the full screen? Somewhere here? No? Anyone knows the full screen mode?
Yeah, it's at the bottom right. You see those magnifying lenses above those. There's the full
one,
that one, and then full screen mode at the very bottom.
Yep.
Yeah.
Okay. And now let me run through this. Okay. I think we were here. Yep. So as I was saying, in this case for the MPI, there is much more communication, and that's why we see that the RECL/NICL communication takes the majority of the time. For this run, it was around 48%, but actually, I think on ASC6 last time I checked, this was even higher, which would then suggest that there is really a lot of communication going on here. So another thing which rockprof v3 can be used for is to generate the timeline traces. So here, in this case, you want to specify the output format pftrace. And of course, before you want to specify what kind of information you want to collect. So here I specified the runtime trace, which is actually a collection of several things, including kernel trace, but also memory transfers and so on. For some smaller runs, you can also specify that there's sys trace, which will be quite a comprehensive and will generate quite a big output. So in our profiling examples, you can do this by also running the helper script traces, MPI traces, and so on. Similar to the PyTorch profiler, this will provide a trace profile. In this case, it's not a JSON, but pftrace with a pftrace extension, which you can open in Perfetto, and I will show the output soon. Another, a bit more advanced thing to note here is that if these traces are getting too large, there are ways in Perfetto that can help you visualize these big traces using a so-called trace processor. I will not go into detail now, but here are some instructions which can perhaps help you in case your traces are gigabytes big and you want to see them. So the output then should look something like this. So this is now opening again in Perfetto, the RockProf v3 Perfetto trace. And here again is the timeline, and we can see different resources, different things happening. So we can see, for example, in this compute agent queue, we can see the activity on the GPU and the actual kernels that were running. Of course, here I zoomed in quite a bit. The actual execution, the GPU activity is not that big, but by zooming with either using your mouse or the key shortcuts, you can see the activity, and you can see also how these kernels are connected with these flows to a specific launch here on a CPU thread. Okay, so I think these two tools, Rock Profiler and RockProf v3, are probably the most useful ones in most cases. I will now also present very quickly two other a bit more advanced tools, RockProf Sys and RockProf Compute. The slides are shared with you, so you will be able to see later more details and also check the documentation. But let me just show you maybe just some basic capabilities of these two tools. So RockProf Sys is really for profiling and comprehensive tracing of the applications, not only for the GPUs, but also for the CPUs. So it collects both CPU and GPU matrix. It provides really a lot of different things like sampling, but also instrumentation, binary rewrite, and so on. Note that RockProf Sys Python support is, I would say, not fully mature yet, but it's really constantly improving depending on which ROCm version you're using, on which profiler version you have access to. This can lead to different experience, I would say. So always the latest one is generally a recommendation to always take the latest one. So on ASC6 to use this, what you need to do is to load ROCm, PyTorch, and then Rock Profiler systems. And one typical ways to do this, to use these tools, would be just to do RockProf Sys run, and then specify maybe some command line arguments like profile to generate a profile, or --trace to get a trace, or to enable sampling, and then maybe use the configure file. Again, always never forget to add --, and only then followed by the Python with all the arguments and so on. So typical workflow for RockProf Sys is in the beginning, and this is optional, but very often used, is to create a config file. With RockProf Sys avail, you will generate a text config file, which is then used each time you're running with your RockProf Sys run. And this config file, you should really inspect it and check what is inside. There is also some nice documentation online. And then there you can basically enable and disable different profiling features. Then potentially you want to do the instrumentation with RockProf Sys instrument. And then finally with RockProf Sys run, you profile your application. So the configuration step here, I think it's important to note that the way you're running your RockProf Sys can be configured in different ways. So one is through this configuration file, another one is through environment variables, another one, and the third one is through command line arguments. Or you can combine any of these. So it's really for your whichever is your preferred way. And then if we run rockprofsys run with profile and trace, it will provide some nice profile files, the text files, which you can inspect, but also the timeline traces, which you can then download to your machine and open in Perfetto again. Here, this trace, the output is quite similar to rockprof v3. The only difference is it also contains a lot of the CPU-related information. If you do the sampling, this can be very useful for some Python applications, because through sampling, basically you are checking what's happening on the whole call stack, and you can then visualize it here in Perfetto. So here I zoomed in very deeply, but you can basically see what are all of these Python functions calling each other and so on. Now let me go to the rockprof compute. So this tool is really for understanding the performance of a single GPU kernel, and this tool has been also added to the ROCm starting from 6.3. The most notable features are the roofline analysis, also the kernel comparison, and there is also support for speed of light and memory charts and GUIs. I will not focus here on GUIs at all. Me myself, I also typically use just this tool just in the terminal, but I know some people prefer the GUIs. So again, to use it, load ROCm, PyTorch, and then rock profiler compute. I mean, these tools, they all come inside ROCm, but just here in the rock profiler compute module, we provided a nice and newer version of these tools. And again, the Python support, I would say, is not fully mature yet compared to the non-Python applications that are more classical for the HPC, but it's constantly improving. One important thing to note with rockprof compute, depending on the version again of the rockprof compute and or the ROCm version that you have on your machine, you may have some challenges with rockprof compute related to some non-deterministic AI programs, which are not uncommon for the PyTorch. The examples shown in this slide should work on ASC6, and the developers of rockprof compute are actually working on a more robust solution in general, but just kind of a heads up for you in case you experience some issues. Also, please let us know. So first thing that you can do with rockprof compute is to generate the roof line. So basically here you say rockprof compute profile, you specify that you want just to generate a roof line, not some other profiling, and it will create PDFs that look like this, that basically some are for the FP16 and int8, other ones are for the 32 and 64. And then basically you can see for different kernels how far are they from the roof line. So for those of you who are not familiar with the roofline model, I encourage you to check the documentation either on the ROCm website or online in general about the roofline. And for those of you probably from the more HPC world who are familiar with this, you know how to interpret it. So basically, this roofline model is a tool that kind of helps you visualize whether your application is more bounded by the memory transfers or by the compute capabilities of your hardware, and how far are they from the theoretical peaks of your hardware. Then regarding the profiling and the analysis of the rockprof compute for the kernels, the typical workflow would be that you collect the profile. You can do that by running rockprof compute profile, and then probably specify the name of the directory where they should be stored. And then the second step here, if you're using just the terminal, would be to run rockprof compute analyze on that folder which you selected. If you just specify this, it will provide you with a lot of tables, with a lot of information about some different performance counters, performance matrix, and so on. There is also an option to specify only a subset of this, and you can do it by here specifying what are the things that you're mostly interested in. A very useful feature for rockprof compute is also to compare different runs. So what you typically do is you run your rockprof compute on your application, you collect the data, maybe then you do some optimizations of your kernels, and then run it again to see what are the performance benefits, and you can then analyze them together using this approach by specifying both of the folders. For the example shown in a repository, basically this will provide the stats similar to something like this. So what we can see here on this main top stats, top kernels thing, is that the initialization and copying buffers are on the top. These are the ones that are taking most of the time. But you can also see some gem or integer gem kernels here happening. And this output in general, I think, is consistent with what we have seen with RockProf v3. Regarding those speed of light tables, so this 2.1, 0.2, and so on, that we selected in the analysis, but you will be able to see something like this. So basically, we can see that for these kernels, regarding the floating point operations, there are none for the FP32 or 64, but there are others in the lower precision. However, these are really, really far from the peak. So this is the percentage from the peak, which indicates the thing that we knew already, that this example is really not occupying the whole GPU. So the performance on the GPU is not that good. There are other ways also for the RockProf compute to analyze a specific dispatch. And you can check that later in the slides. So just selecting a specific execution of your kernel. And then also I added here for the reference a bunch of tips of what are the good ways to use RockProf compute if it's running too long or if the data that you're collected is too big. Also, very often the people ask us questions, okay, now I got my results, but how do I interpret them? Well, here there are a couple of tips of what to look at first, but also at the RockProf compute documentation website, you will have some more comprehensive guidance on how to interpret results and how to look at what are the next optimization potentials. So finally, to conclude this talk, I mean, each of these presented tools has a role in understanding the AI application and performance and how to optimize it. So on the highest level, closer to the application would be the PyTorch profiler, which is the operator level profiler built in PyTorch. Then we have the RockProf v3, which is a command line interface based tool that will profile your GPU activity. The RockProf sys for the combined CPU plus GPU activity. And finally, RockProf compute if you really want to dive really, really deep into the execution of your GPU kernels. And this concludes my presentation. So yeah, I'm wondering if you have. I have, of course, did not check the Discord. I will check it. I will check it later and try to answer any questions there. But maybe you, Bob, or Giacomo have something for me.
There's a question, yeah, from Francois. Has LM cache been ported or tested on MI300 systems to offload the KV cache to the CPU memory?
I really don't know. I would need to check myself first a bit online to learn myself, and then we'll try to get back to you, Francois.
I love
Yeah,
this.
thanks,
We're
Francois.
getting homework from our participants.
Yeah, and I checked about the ByteDance ABQ LLM. I didn't find anything about AMD support. If I find something else, I'll get back to the person that asked. There's no other questions at the moment, but someone's typing. How can I trace cache level activity tracing?
So for the cache, such deep things like cache level, performance counters, and so on, you really want to use the RockProf compute. And with that, it will collect you a bunch of data. And then for the analysis, I don't know by heart, but they're basically different tables. And some of them are really focusing on the caches and what's happening on the caches. So one way to look at this is, I mean, you can either start by looking at the documentation and check which are these tables that you're interested in, or maybe sometimes just print the whole thing and quickly go through it and check later what are the cache activity related performance matrix. Important thing to note, and I have it, I think, in my slides, is so this is how to find information. Then the next question would be how to interpret this. And for that, there is also at the RockProf compute documentation website, there is a page called performance models, which has also recently been upgraded quite a lot. And there is quite some guidance on how to understand some of these matrix which are written by Rockproof Compute.
One more question. Is it possible to trace the various MPI tasks within the AMD profilers concurrently with the various kernels of each MPI task?
Tasks. So, I mean, generally, MPI activity can be traced and is traced by EuroCC. So basically, I have not shown here in the slides, but EuroCC, what it does is it collects all the things from Rockproof v3, but also you can specify some puppy counters, you can specify MPI. It will also run for you the ROCm SMI, so a bunch of things there, including MPI activity. And this is one of the advantages, that you can then see the whole picture, what is happening on the MPI level, combined what's happening on the GPU, because this is what you want to look at when you are trying to do a proper load balance of your application and to get the better performance, and when you're trying to overlap the computation and communication.
Yeah, so I
Yes.
think we'll re-emphasize, we'll go to the chat for the rest of them.
Thanks.
There's some good questions there. So you've seen that there is a particular use for each of these tools, and it's really important to keep that in mind, and also to use the highest level tool that you can get away with, because they actually spit out way too much information if you're just trying to figure out what kernel is slowest.
Yeah. I think that's a good point, Bob, and I would like to emphasize this again. I mean, sometimes, like very often in our cases, since we have Rockproof v3 and then Rockproof sys, which is providing Rockproof v3 information plus much more, and then very often users jump on Rockproof sys because it provides more, but in most of the cases, this is not what they need, and this additional information is just making it harder for them to realize what are the main things that they want to focus on, which is already provided by Rockproof v3, or could have even been provided maybe by PyTorch profiler.
Yeah.
So too much information can really make it harder for you to spot what are the things that you're mostly interested in. And that is why also in general for profiling, you always want to start with a question: what do I want to see from this profile? What type of information I want to obtain from the profiler? And because only then you will know what tool to use and what to look at from the tool's output.
I also want to give a shout out to HPC community tools. So HPC Toolkit supports the AMD GPUs. They've done a tremendous amount of effort to get their tool working with our GPUs, and also Tau out of the University of Oregon with Samir, and Scorpy. You will notice that we have modules for all of those on the system. So those are also valuable, and sometimes one of them will work or give you better view of things than another, or the AMD tools. So we do want to give a shout out to them.
Yeah, I agree. And I mean, sometimes people, especially from the HPC community, are used to some of these tools, so they can continue using them on our GPUs. And also, similar to PyTorch Profiler, there are other Python-based tools which will, of course, as well work on our GPUs, and you can use those as well.
Okay, we're going to wrap up the questions, not because they're great questions, but we're already a ways behind, and I think we've at least covered the majority, the major issues, and we'll take the rest of the chat into the chat. So if I can get Seema online here, we're going to announce the combined exercise and break at this point, and then take a break until the top of the hour. So Seema and I have some announcements to make while we have everybody online. So Seema, you want to start off, and then I will finish.
Yeah, sure. First of all, thank you, AMD team, for your incredible sessions during these days. Um, and I'm starting also with thanks to NCC France as an organizer for this session. Thank you, Marie and Karim, for your support. Also, I would like to thank our team in CASTIEL project, Maxim and Velasta. As well as I would like to announce that we will send all of the participants certificate of attendance of these 4 days. We would like to have also some poll for you to receive your how you feel about this session. We are very grateful if you could take a time to fill the information that we will share with you. If I forgot something, Bob, you can also include your part.
Okay.
Thank you.
Okay, so we're gonna, a couple other announcements. We have an upcoming CASTIEL HPC training October 28th to 30th. And I think we'll have that posted in the chat here and on both chats here on how to register for that. It will be, again, 3 half days covering HPC topics. The workshop system that you've been using will be available until the end of the month. There will be other workshop events on it, so be considerate, but it is available for you to try out and to work through some of the exercises. There really are more than you could probably do unless you're working on that full time. The slides are public. They can be shared. We do ask for attribution, but more importantly, don't make statements that that might be implied that are AMD statements that might be negative for other vendors or comparisons of performance. Recordings will be available later. These take time, and this is an incredible service that the organizers provide, and it just takes a lot of time to do videos and edit them and cut out the right parts. And we really do want the poll for the workshop. Give us feedback, what you want. And there are text fields in there that are quite often the most valuable. You know, how can we provide more information to you, and what kinds of formats would be useful to you. With that, there are exercises in the handout that you can jump to and try out these tools, and we'll stay online, and we'll see you at the top of the hour. Anything else, Seema? Giacomo?
Here you have, please take your time and feel it. Like it is here in WebEx app. Mari already shared with us. You have 30 minutes. So thank you very much for your feedback. It is very helpful for us. From my side, I'm okay. Thank you. Giacomo.
And yeah, and I just wanted to take a second to thank Luka for a great presentation. And, you know, there's a limited time that you see people present, but there's a lot of work that goes behind the scenes, and he's done a great job organizing everything and making it effective for you all. So we really appreciate that. Thanks, Luka.
Thanks to the whole team that helped.
Okay, so for the next one, we're gonna have Bob tell us all about inference benchmarking.
Yeah, Sadafa, are you going to help with that one? See if Sadafa's online here.
Bob, you're presenting that one. Sorry. I mean, yeah, sorry.
Okay.
I'm sorry.
No problem.
I'll come back.
Okay, I got to get it downloaded then.
Yeah, Siddhartha has been very helpful with getting a lot of content ready, but he's busy with RFPs and other activities. So the fact that he's here is already great, but unfortunately we cannot pull him too much.
Okay, I got to get it from my mail, I think.
Send them to you on Teams as well, though I know if your Teams is working right.
I think it's better. Okay, so we're going to open the PDF and hopefully it'll behave. I trust it more than a PowerPoint right now. Okay, so we're going to talk a little bit about an AI application that, and this is actually a whole series that Sadaf has been working on producing on a deep dive into how to do some optimization of a real workload, small workload, but a typical workload. So we're going to start with inferencing in this talk, and then the next talk will go into training. So inference is using the network to make predictions on new data. So often you can think of this as, what is the next word that follows the word that I currently have in my question? And it keeps adding words and composes an answer to you. And that's basically what the LLMs do. And so this is the heaviest use right now in the AI tools and what everybody is so excited from. So to do this, they have to build correlation or neural networks of associations between words. And the better you can do at that, the better the results. So the differences from training is that it's using the table that already exists, that association of words in a table, at least conceptually, that will allow it to make that prediction of the next word. And it's generally been a lighter weight requirement on hardware, although some of the newer advances have stressed the hardware as well. So usually the workload requires a lighter compute hardware. Only part of the layers of operations, and smaller batch size. So it generally, at least today, it doesn't require quite as heavy a compute capability. And so this is probably we're doing more inference where we're using the data that is put into this association table. We're going to use that data many times. So inference is going to be the more common case, and then training is going to be done periodically to provide that association data table. And we have a lot of different options in the inference space of, can we use a smaller model data? Is that sufficient for us? And then we can run it on a workstation GPU, or do we need heavier weight hardware to do this operation? And we found that when we first started exploring the smaller models, which we started with just because it was easier, that the results were not all that good. And using the bigger models had a noticeable effect. Even though AI workloads are heavily optimized, they're still only running at a fraction of the hardware performance, especially if you just place it on the system without any consideration to do any optimization. So what this process we're going to go through today is to increase the samples per second. What does that mean? Well, if you launch a query to that open web UI that we've provided you, if it takes 2 minutes to respond with the first word response to you, it becomes much less usable. So we want that response to come back faster. And better hardware makes a big difference there. GPUs are much faster than CPUs, and bigger GPUs are faster than workstation GPUs. We also want to reduce the memory usage so that we can run this on a smaller device. And then we want to combine these kernels, fuse the kernels to reduce that gap. I think Samuel showed that in some of his presentations, that you get these gaps between the kernels, and we want to fuse those kernels and maybe get some overlap in communication and computation. So we're going to go through how you do this optimization cycle. And none of us are complete experts at this. If you reflect back, much of the software didn't exist 2 years ago. I mean, TensorFlow was still the dominant framework. And so, you know, even a couple months, things change drastically. So we have to also stay up with what the new developments are, because there's a new package coming out every month that speeds up part of this, one aspect of the whole process, the compute process. So we're going to look at a lot of different items when we do this analysis. So here are some of the metrics. You know, throughput, how fast is it responding? You know, what is the delay for both the response and for each operation being done in the compute cycle? We'll look at memory usage. Kernel count actually is surprisingly important in these, because they break up all these operations into composable units. And that means that some of these kernels are small, and if you can combine them, you can really make a big impact. Bandwidth, of course, we're still memory limited on a lot of these operations. So organizing the memory, getting better bandwidth can be really effective. And arithmetic intensity is a key metric to understand where you are in the performance landscape, whether you're being limited by loading data, or what we call the feed and speed. So how fast you're getting data to the system and how fast the compute is. And GPU occupancy as well, although I think that can be overused a metric in many cases. But we really do need to expose the parallelism. And if you think of that occupancy as more, I got more units of work to spread out, that can make the GPUs much more efficient. In the case that Luka was showing, that was a small problem. So there wasn't really enough work to keep that GPU busy. So these are good pitfalls to think about. You know, don't launch into the optimization early on. You know, know which kernel you need to spend time on, rather than just blindly going in there and doing optimization. I think also numerical accuracy and reproducibility are really important. Now these workloads often have an inherent randomness to them, but you still want to, if you turn that randomness off, you want to get the same results on different GPUs, on different number of GPUs. So that's a real key thing that's been ignored way too often in the rapid development of AI frameworks. And so pitfall 3 is, again, that optimizing the wrong operations. And you know, if you take a workload from the NVIDIA hardware and move it to AMD, or AMD to NVIDIA, and you say, well, it isn't performing as well. Well, it takes a little while to tune it for each hardware device. And the priority actually is to keep it portable first, so that you can move from system to system and then apply tuning that is that's still somewhat portable, so that you're not breaking your workflow. So we mentioned a little bit about the different profilers that are available, and so here's a few parts of the profiling ecosystem. Heavy reliance on the PyTorch profiler is really suggested. It's the easy thing to get data from. The only thing easier is if you have your own timing in your Python code to get the high level timing output. You know, and then PyTorch Profiler is probably your next option you want to use. The Deep Speed Profiler is probably your next option you want to look at. And if you're really doing a deep dive of how to get the most out of the system, this micro benchmarking can be very, very useful. And I know we've worked with some groups on the micro benchmarking, and they're not necessarily getting good results right away, but then we show them things like the PyTorch environment variable to tune the gems, and all of a sudden they're getting much better performance. So that can help you understand how to tune for that hardware. So I'm going to give you an introduction to the hand-on exercises. So this is really example driven. And so you can look at the, if you checked out the examples, you can look at this inference benchmark and walk through these steps. And I'm just going to briefly go through these and make comments about them. So you do need to get on a GPU node. For this, you probably only need one GPU, but we're showing get 2 GPUs here. You also need to get CPUs. Why do you need to get CPUs? The amount of memory you get allocated is proportional to the number of CPUs you request. And that's what Slurm does for you. And so if you're on the Perry Peak nodes, there's 192 CPU cores. So you can take, if you get 2 GPUs, you could reasonably request half the CPUs. Now, if you don't need them, there's probably not a need to allocate that many, and you might leave it for people who are doing other work. Check, you know, doing some quick checks are always useful. I can't tell you the number of times I try to run an example and I don't realize I left out the option to request GPUs, or I'm on the front end. So that's always a good thing to do. Check ROCm info, make sure ROCm info is on the system, look at the status of the GPUs. And if you run these tools, you'll see, you know, some message about each of the GPUs and what the utilization is on them. You can also get the temperature. That can be really helpful to check the health of the node before you do benchmarking. And then when you load PyTorch and ROCm, and on this system, it's hierarchical. So you load ROCm, then PyTorch, and PyTorch will load OpenMPI. But we do that import torch to make sure our paths are correct out of that module. And then we check that Triton is working. You can go much deeper on these checks to make sure everything is functioning. And so this is, I'm not going to go through this step of verification of the installation and all the other exercises. And this is particularly useful if you are downloading a wheel. You know, what is in the wheel? Is the path right? You know, or a container. So so this is always a good step. Make sure everything's working. So here's our workflow that we're going to do here. So we're going to establish a baseline, and in this case, we're going to measure that and try to understand within the default configuration what kind of performance we're getting. And then we can do this sort of parameter sweep where we change the batch size or reduce the precision. And here that will make it faster, but we also need to be careful that we're getting the proper results. And then what kind of optimization flags we can use. And we try to identify the bottlenecks. It's not just that this part of the code is slower, but what is causing it to be slower. So we, starting off with the simple optimization, such as those MI open environment variables, the PyTorch tunable ops, maybe using a different one of the PyTorch friends for one of the operations. Those are the kinds of things you want to do that are not too intensive change of your code. And then we just do this cycle of running the benchmark again, seeing where our next bottleneck is. And we really strongly recommend keeping notes on this process. You might have to do it on a different system or a different workload size. So, keeping good documentation is really helpful. I do want to note that Sadafa has done a really good job in the markdown documents of having places to take notes and follow along what's happening as you go through this process. This is the first time we have shown this presentation and the next presentation, so they're a little rough in places, and we're still trying to reorganize the markdown documents and create the slides to go along with them. So here we can add the Torch profiler. It may be a little confusing because we say some of these say CUDA, but they really mean GPU. So again, CUDA was the first thing that was included here, and but we now support these as well, and the community supports it. So we're going to start running the benchmark using our micro benchmarking tool here, and supply, how many iterations we want to run. We can add these optional arguments, so we can add these to enable the PyTorch AutoGrad profiler or the Kinito profiler, or the deep speed flops profiler at a particular step. Now, I haven't even had time to experiment with all these profiling options, so I strongly recommend that you do that on the system while it's available. We can use Torch Run to run across multiple GPU. That allows us to run multiple GPUs as well as a single GPU. So you want to first start out measuring the performance on one GPU and then start looking at the scaling both within the node and then to multi-node configurations. And there's many options in all of these AI frameworks that will do an optimization with just a flag or an included line of Python code. So here, this is showing you can optimize the graph just by adding this runtime argument in PyTorch 2.0. We're looking at this output from the benchmark run, and we notice right away, why is the runtime slower on the first iteration? And this is not uncommon in any workload that sometimes the GPU has to wake up. Sometimes kernels have in these frameworks. Sometimes the kernels are being compiled the first time through, or allocating memory and populating the cache system. So we usually recommend a warm-up cycle before looking at the performance numbers. And you can see here that the first iteration is considerably slower than the second and third. And then we see it sort of stabilizing. This goes through the different kinds of metrics that we might be taking a look at and I think I've talked a little bit about this, so this is just a deeper dive into that. So we can, we're basically trying to get, the number of samples processed to be higher. So we're going to watch that metric to see if we can find a way to boost that up higher. And batch size is one of the things that we can look at. The latency, we want that to be lower. Memory usage, this is actually incredibly important. And I'll point out that the Instinct GPUs, the MI300 has 128 gigabytes of memory, which is higher than some of the NVIDIA GPUs. But the MI300X has 192 gigabytes. So you have if you're on that kind of a system, you may want to put more work on a single GPU than you would elsewhere. But conversely, if I can get my memory usage lower, I can run this on a workstation GPU. So we really want to look at the memory usage. That's actually really, really important. And then we want to look at the utilization, arithmetic intensity, what percentage of compute, what percentage of the theoretical bandwidth we're getting. So this goes into batch size. So we're going to look at batch sizes ranging from 8 to 256. And at some point, you're just going to run out of memory. So you want to find the optimal amount. How much can I do on this GPU to use the GPU effectively? And so this is showing a comparison of, and the row is filled in for 32, and it's your exercise to fill in the rest. And I do want to warn you that these numbers come from different GPUs. And so you will get different numbers here depending on what GPU you're working on. And I don't know, there's actually not many of these were obtained on an MI300A. So some of them might have been updated for that, but many of them were originally on some other GPU. But the relative performance should be similar. So precision comparison, this is what's driving all this attention on lower precision, and where you can use that can be a huge benefit. But there's also cases where you want the higher precision, as we've talked about before, particularly as we move to AI for science. And so using a lower precision reduces the memory usage and should speed up the operations. So here is a table showing a comparison of performance between floating point 32 and floating point 16. And we see almost 2x faster, which makes sense. And a pretty good reduction in memory usage. So here's more on that comparison of precision. And so this is how you would run it with FP32. And there is a mistake, I believe, in that first example. It's also saying oh no, it's turning off FP16 with the 0. And that will make it FP32. So, and in the second one, we have FP16 set to 1, so that's going to turn on that FP16. This actually makes a lot of sense that, we've reduced the precision. We're going to have a comparable increase in performance. This is somewhat different than the CPU. In earlier days where you would change the precision and thinking, oh, I'm going to get a 2x performance increase, and it generally wasn't all that big a performance jump unless you were using the vector units. And the vector units are very similar conceptually to the thread engines on a GPU. And so we do see a big jump in performance if we can go to lower precision. So here's running the PyTorch profiler. So we can add that autograd-profiler to our command line, and we're going to get a lot of results like you see over on the right. And it conveniently shows you the ones that are taking the most time at the top. It does take some time to dig into it exactly what's happening, but here we know we need to focus on those top 2 or 3 items in our first optimization steps. And we can look at, it's often you learn more from doing a comparison than just getting a single output. So here running 32 bit versus 16-bit will give you a lot of ideas on why you're getting those performance jumps. We can also run the deep speed flops profiler. And so this is going to compare, especially the matrix multiplies, what the achieved flops are versus what can be achieved on the system, or what the theoretical limit is on the system. And that gives you an idea, and we'll show that a little later, do I have an opportunity to improve here, or is my current performance good enough? You can also, because these AI workloads are very, each part of it is something you can quantify. We can calculate the flops analytically and get a pretty good estimate of what's going to happen on the system. So here we see we're counting up how many flops are in that matrix multiply, looking at the theoretical max for the system, and that's going to vary depending on what GPU you have. And then you can evaluate how you are doing. It's very difficult to get to 100% of the theoretical performance on the system. So certain kernels in these workflows will be close to the compute bound limit. So understanding which ones those are and how we can optimize them can be really important. For example, if I see the matrix multiplications are slow in relation to the roof line, the theoretical limit, I might try that PyTorch tunable ops and see if I can boost it, measure it, and understand how much performance improvement I'm getting. So here we're going to do the flops profile at step 10. And so you can do this exercise as well. And so we're going to go deeper into this compute versus memory bound. That's also heavily utilized in the HPC world. There's actually a lot of commonality between HPC and AI that isn't aware to each of the communities. So we do have, I believe we have deep speed installed in our module. If you're building your own wheel, you may have to do a install of deep speed. And then we can run that flops profiler. And so this is doing it at iteration 10. And as we showed earlier, we really don't want to do that profile on the first iteration. We want something a little further along when it gets stable. So this is a reiteration of that cycle of optimization, profiling, optimization, and validation. And we did have some questions in the chat about, where do I get guided analysis on this? And we have found actually asking the AI profiling or programming assistant for ideas can be quite helpful. And so you might try that. That may be your best tool today. And so then, you do want to document where you're getting that performance. Might give you an idea where to look in the future as well. And this is just a summary of what we've talked about before. So some methodical approaches are really recommended that you document this and keep track on the system we are on. for this workshop. It's a shared system. You can get exclusive GPUs, but your performance may vary. And this is really a pre-production part, so it should be close to a production MI300A, but you may get some variation, especially if they start running hot. They may downclock since these are air-cooled. And with that, we'll post the disclaimer and third-party trademarks. And I think that's it for this presentation. So do we have questions that should be addressed? I got 2 screens, 500 windows, and I can't find anything.
There's a lot of questions coming at Luka from his presentation. I think, the last one too is probably for him as well. He's been very active getting back to people.
Yeah, and we're in this presentation on the inference, we really focus more on the framework level tools, but your next level is actually to use RockProf Compute, RockProf Sys, RockProf E3, and dive in deeper on what's going on. Okay, I think on our schedule we had some time for exercises, and then a break until 3:50. So I think really strongly recommend run some of these exercises and get at least familiar with the workflow and what data you can get out of these tools. And Sadafa may have had to drop off. We do really appreciate Sadafa creating a lot of this material, and wish he had time to actually do the presentation. We've also had a tremendous effort from some of our profiling tools collaborators, some on this call that have been checking that the AMD profiling tools work on these workloads. Okay, I think we'll take a break here. Exercises and break. Your exercises can be on the computer, or you can do a little bit of stretching, or both, I would recommend. And we'll start back up at 15:50. Oh, she's got the coffee.
All right. Thanks, Bob.
Okay, it's that time again. Really appreciate everybody sticking through all the presentations. It's quite a long time, and yet we only cover the bare essentials in this space. So I'm going to go ahead and share. I hope Giacomo's gotten some coffee, and
I got the IV, yeah. Brava, Sima.
Yeah. I really appreciate our organizers, Seema, Marie, and Kareem, Lesta. They've really done a great job of organizing this. It's a lot more work than people realize, and to pull it off well. Okay.
It's a great pleasure.
And I do another call out for the HPC workshop in a couple weeks. And the other workshops that CASTIEL is putting on. I really say we talk about power walls and memory walls and all these other issues with HPC systems today, but the real wall is human knowledge, is knowing how to optimize for these systems and make it run. So these things are really important. Okay, so we're going to be talking about this tiny llama example, and this is going to be going into the training type of workflow. So this is a fairly small problem, but it's designed to do some quick exploration. Let's see if I can get the chat up. And there's some great recommendations in the chat about more advanced ideas. This area is changing rapidly with new ideas for optimizations and how to unlock the potential of the GPUs. So I strongly recommend following the chat and looking up some of those references. We are getting our homework assignment to look into those as well. So let's dive into this one. So in the tiny llama example, it's a large language model, and it's really designed for education. So we're focusing on, understanding the different phases of the workflow for training. And I'm learning as well on this. It's, the amount of deep dives that have come from researchers in this area can take quite a bit of time to understand. We're going to look at profiling and optimization, and also understanding the hardware we're running on for, in particular, the AMD GPUs. And so we'll launch into that right now. So there's a couple configurations for this. The one we will be looking at is the small configuration. There is a medium configuration if you want to get to a bigger problem. We did see on the GPUs we tested, we saw through this process almost a 6x performance speed up. Now, I'm only showing you presentation 1 of what will eventually become 4 presentations. So we're just unlocking the whole workflow that we're going to be looking at in the future. But we need some time to clean up the slides and the process for this training system. So as you do your profiling, you should get some speed up on whatever GPU you're working on. Even a workstation GPU, you should see some speed up on there, but it's going to be different than this one. So this is really a fairly standard workflow for doing training. And the first step is embedding, and this is really breaking apart our data into tokens. And that gives us what they sometimes call a vector that we're going to process later on. And then we apply this RMS norm and rotary position embeddings. And I'm still learning a lot about these different optimizations and modules in the workflow myself. And then we have multi-head attention, so we're actually going to use multiple paths to encode these queries, this vector of tokens, and then we use this sigmoid function, so really an activation function that looks like an S. And so when do we want to, in that association matrix, we want to have the proper level of association between items. And if we have them all very high and all very low, it doesn't really differentiate very well. So some of these optimizations are to encode the information that gives us a more effective result in the inference step. And here's sort of a flow of the whole thing. And this inner loop here, I've shown in the vertical dimension, because it wouldn't fit on the whole page, but this is showing how that each step along the way, and you will see some of these steps are done at multiple places along the process. You also see this attention where we show 4 items there, and that is your multi-head attention. And then we end up with our output from this inner steps and then output from the whole process. So we can compute the computational complexity for all these steps. Not going to go into detail on all of these. There is quite a bit of information in the markdown to help step through this. but I think it even needs more detail than there, where you get these numbers from. But we can come down here and we can see for a forward pass, we're getting 1.34 gigaflops. And, that comes from all of these numbers up above. And we're not going to worry about really all the details in that. We just need that final number. And then we can compute the bandwidth requirements. So here we get 11.2 megabytes from this part and 50 megabytes from the activation memory, which gives us a 61.2 megabyte quantity of memory that we're processing. And so then we take that and combine it with what we got from the previous page or previous slide, and we can compute arithmetic intensity. Why are we doing this? So this is sort of our back of envelope calculation as kind of a sanity check for some of the output we're going to get from the profilers. And it also allows us to perhaps do something like evaluate if we change those 4 bytes to, if we go to FP16, what is going to be the effect of this, or changing the batch size. Here is the roof line that comes out of the RockProf compute, showing where all these kernels are. And this first slide, I just want to point out the roof lines we're concerned with, because this tool currently shows you multiple roof lines, and we need to know which one is important for us. So since this is a single precision FP32, we want this turquoise line up here for the matrix multiply, the matrix unit up at the very top. For the bandwidth, we're using HBM for FP32, which is this purple line here. And you notice our kernels, they're not horrible, but I do want to point out, and we'll see this, I'll go to the next slide. So the way this thing puts the information out, it shows this roofline plot, and the list for the symbols is on a separate page. So I've included that here, and also added text to show you where each of those kernels fall. And let's go to the next one, because I'm going to dig into deeper each of these different sets. So we have matrix multiplications here, and those are close to the compute roof line. So we have enough, and we said 21.9 flops per byte. So we're, that's right in line with where these are showing up on our plot. But we're still considerably below the roof line here. We're close, but remember, this is a log-log plot. So there's still some room to improve. So that you might actually try turning on the PyTorch tunable ops and see if this changes. There'll be other things that we do to try to improve it. We do see a much bigger gap for these other operations. The matrix multiplies are heavily optimized. These other operations don't get quite that much attention to optimization. Those are not using the matrix unit, so that's the value FP32 line. And there is a considerable gap here, but we also need to look at the gap to the bandwidth. So we're sort of at that transition point where it's a compute bound versus a bandwidth bound kernel. And that tells us we could probably reorganize the data in a way that would load into the GPU in a better fashion. And then we see these element-wise kernels down here, they're really bandwidth bound. And there's still quite a gap between those and the roofline. Those probably aren't as important just because they're not as large a fraction of the overall runtime. But that doesn't mean that you can't get some benefit from looking at that at some point. So, we've got some parts of this that are compute bound, and you know, that gives us an opportunity for some optimization. We could probably improve things from kernel fusion. We sort of already commented memory layout would help us get close to that memory bandwidth roof line that's on the slope. And here's a couple ideas where we might try to do some optimization in the second and in the last half of this slide. So we might look at all of these ideas to improve the performance. And don't get discouraged with, I mean, we've talked about so many optimizations, both on installing the software, in how you write your Python code, or options you provide to these frameworks. You know, look at what the potential gains are from each of them and how much effort each of them are, and pick the ones that are most important. You don't have to optimize everything. Here's a lot of references for each of these modules in the workflow. And you notice these are all fairly recent. I mean, I think the oldest one here is 6 years old. So a lot of new developments in this field, and frankly, you know, we could probably go through the research literature and find a whole bunch more that are just starting to show up. So this is our first presentation, session 1. So we're just benchmarking the base workflow, and in the future we will have 3 more presentations, and this is just sort of showing the improvement as we go through each of these steps. So we're just going to be measuring baseline, understanding the performance limits, the where we might look for optimizations, and then the next ones will actually step through some of those optimizations, and you see you know that we get around a 5.8x speed up going through this whole process. And we also see a reduction in memory of almost 2x. So that can also be extremely important. This is just a summary of the sizes that we're using. Now, we probably pull from these sizes to compute that computational complexity and the amount of memory that's needed. So we're just showing these as we will need these numbers to compute those calculations. We're not going to do that in this presentation, but we do note that, so that if you dive into the hands-on exercises, the markdown documents there, you know where to pull these from. So we're going to now dive into the exercises, and here we're going to pull that tiny transformer, and we're going to look at version 1 PyTorch baseline. We're going to get, we really only need 1 GPU here. We're showing 4, and you probably want to add dash CPUs to get the memory, or specify dash mem to allocate memory. And we're going to get our baseline performance here. So we're just going to run that tiny Llama script that's already in the examples there. You don't have to create it, and just run this first one to make sure everything's working and to get our baseline run in. And then we would free the allocation. Now, what is the sample output? We're going to get something like this from the output from the run, and there's a lot of numbers here that we can utilize to understand the performance. We were missing a make dir on the PyTorch profiles here, that you make it an error and need to create that directory. So now we can run with the PyTorch profiler, and again, we can get ourselves a node to run on, load the modules. And here we're just going to do that enable PyTorch profiler and point it to a different profile directory, so that we can do the comparison of these runs. keep each of these in a separate directory as we step along. And we again get this output, but we want to see what the PyTorch profiler is giving us. What things do we get from that? And we can launch TensorBoard, and I want to thank Marius for getting these screenshots out. You run TensorBoard. This bind all will allow remote connections. And then you use the similar SSH tunnel command that we did for the Open Web UI interface. And Marius was only able to get this running on the login. You may need to install TensorBoard in the Torch plugin. I don't think we've added that to the PyTorch module yet. And then you open your browser and you can see the output from TensorBoard. And this is an example of what you get out from that. It gives you a nice visual output, and broken up by different information on the system, so you can explore, click on this, and get more information on each of these items. So we're seeing, the memory movement. We can assess whether that's close to our estimate, and confirm. This is on a peri-peak node. So this is just the first screen of the output. We can also get sort of a timeline profile, and this is showing the different layers that are operating, the transformer layer, the attention layer. We can start to get an idea of the relative performance of each, and maybe get an idea how we might optimize this. Now, the pictures are great, but it's also good to have numbers, and so we can get some hard numbers on each of these that we can feed into our analysis. And what's kind of nice about this is the pie chart, giving us, which ones are taking the most time, both in total time and just in that routine. So we can see your attention is one of the ones that is something we need to pay attention to. And then it gives this table of output. And if you look at this, the font is small, but we see a bunch of these CIJK, AI, AILK, BIJK. Those are matrix multiplies. And we see several of those on the list. And so the matrix multiplies are a significant part of the runtime, as expected. So now we can do, we can look at the memory analysis and turn on that enable memory profiling and put that in a separate directory. And we can do that for batch size 4, 8, and 16 and analyze how changing the batch size affects the memory usage and the performance. And again, we can launch that TensorBoard, get the graphic view of what's going on. We can also vary sequence length. So here we have sequence length 64. We can also do 256 and 512. So you see we're sort of doing sweeps of the parameter space to see how that affects things. And those are easy things to change. So that's kind of the thing we want to start with, is what is easy. We can analyze our bandwidth utilization, and we can grab the bandwidth metrics from this JSON file with this simple Python program. You might have to do Python 3 on some of these on our system. So once we've done that, we can reassess what we think is the best selection and do a bottleneck analysis. So what's with after doing that sweep and getting good selections for each of those, now we reevaluate. And we can get that performance summary report from that directory we just ran. the profiler also gives us a way to generate a report and a detailed analysis. So that may be another thing you want to try. Here's our flops analysis. So we can, similar to the bandwidth, we can use a small Python program to get that out of the JSON file. And then we can finally do computational intensity. So we want to know what the arithmetic intensity is and evaluate it compared to what we estimated at the start. There's some issues you might run into, especially if you pull down a wheel or you're using Conda. Conda does not have the GPU-enabled Triton, so you may want to reinstall it by doing this pip install upgrade. Also, you may want to clear the cache. That might be important, especially between runs, partly so that you don't run out of memory, partly just to avoid, you really want a clean system before you do a performance run. And next steps, so we've now got our baseline. We're evaluating where are we going to go from here, and we're going to actually do these steps in the second, third, and fourth presentations, which we will not do yet. But this is where would we go. So we're looking at what the optimization targets are. So what can we do in attention? We saw that was one of the higher time-consuming operations. So we see 3 kernel launches there. Maybe we can optimize that. For the FFN step, we see 5 kernel launches. So can we reduce the number of kernel launches there? So we got kernel launch overhead. We got memory layout we can look at, and also optimizing the gem. We can also do some things with the memory storage with the intermediate data that comes out. So there's a fair number of different optimizations we can do at this point, and those will be in the next presentations. There are markdowns for these presentations 2, 3, and 4, called version 2, 3, and 4 in the markdown. They are a little rough, but you can follow along with them if you want to dive deeper into these optimizations. So we've done that baseline profile. We're going to focus on the ones that are the most important. In version 2 here of the presentation, we're going to do the kernel fusion. And then 3, where we saw the biggest jump in performance, will be custom kernels. And then 4, advanced fusion. And we'll evaluate the impact at each step along the way on our GPU. So that concludes the presentation. And I think at this point, we can take questions and give you an opportunity to try this exercise.
Bob, there's a question in the chat saying, I get a TensorBoard comment not found. They're asking
Right. You got to do a pip install TensorBoard and plugin. That was on one of the slides. So we didn't quite get that installed, Giacomo. We try to install everything, and this is the problem if you pull down wheels, is there's a lot of little things you gotta. Let me see if I can find the slide.
We'll add it to the shopping list and install it tomorrow. Yeah, we've been trying to not act on the system too much these 4 days since we didn't want to cause any disruptions, but starting from tomorrow, we'll do a little bit of activity on it.
So you may want to create a virtual environment for this and do a pip install TensorBoard and the Torch plugin. And that's something that Marius commented when he got the TensorBoard to work on the system. It's also a little inconvenient, getting graphical output off the system, and you may encounter some issues there. So how would I deal with that? Well, you could actually install this on your workstation, bring the files over and view it there. But I didn't do that because it takes a little bit of time.
There's a question that I like. How does one check for correctness after each optimization? Which is a very HPC-like question.
It's a good question. If you saw the coarsest way to do that is if you saw Giacomo's presentation as they were working through the BitNet package and getting that working, is you supply it a simple question, and if it gives you garbage, well, it's a repeated answer instead of a correct answer. That's your first test, but that's not a rigorous test. It's just a sanity test. And it's a little more difficult to do a rigorous test. You'd have to turn down the randomness on your model and see if it gets the same data out. You saw also we did some tests in the RAG where we gave it a query that we knew was in the RAG documents, but not in the LLM to test, and that it was actually getting information from there.
Someone in the chat has suggested checking the figure of merit.
Okay.
We don't have any more questions at the moment. This is your chance, folks. We've got only a handful of minutes left. Last day.
Yeah, I like this comment. Writing a simple unit test won't cut it. And I think that's why there has been a lack of focus on correctness in these models, because it's not all that simple. And so they just sort of say, hey, it gives me something that seems reasonable. That's not really good.
Yeah, it's always a fun conversation to have. Right?
Yeah, and I like this comment about looking at the figure of merit and looking at the training loss. Is it converging?
We want to see the convergence with the expected order of the finite element approximation. That's what we want to see.
Oh, yeah. Yeah, and I do think that we have some in the audience that are probably done a lot more work with these workflows than we have. But we do want to summarize, that for the general community. I think it's also good to document it because you don't find many places that it gets all put together.
Yeah, and I think we probably have already mentioned it, but our repos, the one with the installation scripts and the one with the examples, those are public, of course, and we welcome contributions. So if there's any one of you that has examples that you think might be relevant for us to include there or to show at future events, please make a PR, and we'll look at it and we'll include that in our offering. If you have installation scripts that you use that are custom for packages that we don't have, send them over. We want to crowdsource, and we welcome contributions.
There's a PR sitting there waiting for you to merge it.
I've been talking to that person on Teams. Yeah, yeah, that's for Rock'em on Windows, so it's something that's interesting to include as well.
Yeah. So we have a comment that you will have more questions as you go through the exercises, and it takes a while to go through them, which is why we make the system available for a while and why we want to chat, which persists a little longer than just the presentation. It's also really valuable to have the videos to look back at, because there's a lot of technical material to grasp all in one pass. I do also want to mention you can view the videos generally there and have it translate it to the captions to a language, a language of your choice. And Giacomo's played around with that and says it actually works pretty well. I think that was in the Chrome browser, right?
Yes.
And I do want to comment a little more on the figure of merit and the training loss. Those do vary to some degree. So you can't just say that you get exactly the same number out, but it should be within the same order of magnitude. Okay, we're into the exercises, and I hope all of you have found the exercises and how to get around on them. Here is the PDF version of the exercises, and here's the inference example that we went through with the PyTorch profiler, the AutoGrad profiler, the FLOPS profiler, and then this last presentation is this ROCm tool. Well, yeah. And so this is going to go through how to do that version 1. And then it goes over some of the architecture and computations to estimate the bandwidth and computational complexity. Some technical appendices which go into even more depth in the theoretical background. And then we get to our PyTorch baseline. So starting on page 94, you can start going through those. So this is our baseline performance analysis, which this is basically what was in the slides. And you can step through this. There's a few differences. We added a bind all on it and also put it in the background, and then launched our browser with the SSH tunnel. And then we have our batch size scaling here. And this shows doing it in a loop, a few more sizes than what we showed in the slides. And there's some repetition in these markdowns where a slightly different version of the steps is shown in a different markdown file. Some of these were mention how to install the tools or the PyTorch and the tools that are necessary in PyTorch. So you may need to do that if you're on your workstation. We've tried to simplify it by having these pre-installed, and then it shows sample output for some of these. And the analysis, which we didn't really go into, but it goes into much deeper detail on the analysis, the numbers that come out, and some troubleshooting. And then it gives you a space to record your information from that. So it's actually a really nice document to walk through things. With that, I think we're going to stop the presentation of the exercises and give you a chance to get on the system and try it out.
So let's say we reconvene in 20 minutes.
Okay.
And, final goodbye.
Right, and we'll vote for the best question, right? The one that stumps us.
I think Dr. Kirikou has very good points.
Yeah.
That's Siddhartha.
Yeah, and version 2, 3, and 4, we're going to start using the AMD profiler's a little heavier. In here, we've really stuck with the frameworks in this first step. I'll take a 15-minute break here. Okay, we're going to close out right now. There's some good comments. I really appreciate Gina Sitarman answering a lot of the detailed questions on profilers. Gina's been working really hard along with her colleagues, Luka, Ian, and others to get the profilers working and to chart a path forward for them. So I really appreciate that. I want to thank our organizers, Seema, Marie, Vlasta. Thank you so much. And Kareem. Where did Kareem go? We wore him out. But we want to thank you all and really appreciate it and making this very detailed dive into AI workflows enjoyable and fun, because it can drag on quite a bit. So thank you.
Thank you.
And of
Thank
course,
you to the great speakers.
and
Thank you. Congratulations.
I do want to really celebrate Hugo. He got TensorBoard working. Sometimes those steps are a little bit difficult to get working, and I didn't get it working. So Hugo, you're ahead of me. Anyway, we're going to wrap up. Seema, Marie, do you want to do any thanks and close out too?
Yes, sure. First of all, I would like to thank you, all AMD team, Bob, Giacomo, Jose, Marius, Alessandro, Samuel, Luca, Gina, Sidafa, Joanna. I think I could say all. Thank you, all AMD team, for great effort and your time to wake up like early morning or in the middle of night. Thank you very much for all the effort. Really, it was a great pleasure to work with you. And also great thank for NCC France, Marie and also Karim for this organization. Thank you, Valesta, for your help and being part of our group. And also thank you all participants to be here. And I hope you enjoy these 4 days of the AMD training. And we are waiting for you to come for the next one, HPC training, that we share the information with you. And I hope you enjoyed. And thank you all. And we can close the session and see you soon. And we will share the video as soon as we have it. So we would like a little bit of patience because it will take time. And we will try to send also certificate of attendance as soon as we have it. And meanwhile, if you need anything, you can pin us in the Discord channel and we will come back to you. If I forgot something, please, you can you can add your comments.
It's perfect. We are all waiting for you for the next session, and we really enjoyed this one, so I'm really waiting for the next one. So thank you.
Thank you very much.
Thank you.